right, good morning, everyone. Hope you're all doing well. A couple more people coming in. All right, great. So we're gonna continue on. Reminder here, make sure to get your first lab done for the 6th, which is Sunday, and I know Labor Day is Monday, so we won't be meeting on Monday. Lab is still due Sunday, but you don't have to wait until Sunday to do it, okay? So if you want, get it done sometime this, later on this week, because I probably won't be answering emails Sunday evening, just because I have a life too. So just make sure to at least sort of chip into it and like figure out what you don't know how to do before weekend begins. Okay, so we left off, let's see, chapter 2. Let me share my screen with you all. All right. Oh, and as far as submitting the lab in Moodle, make sure that you are submitting the experiment here. So you will fill the lab out in your paper lab manual. You'll take a picture of it, or if you have a scanner, you can scan it. Someone told me that you can use, there's Adobe has its own free app, so you can use that to scan on your phone, but you'll then submit it here. If you're having troubles uploading things, how to submit a lab online, there's a little video right there from Glenn Radcliffe, one of the other instructors, that makes it real simple for you. You also want to make sure that you do the quiz associated with it, okay? You don't do quiz 1 because we don't have any lab safety stuff, but I do want you to do quiz 2, okay? So make sure those 2 things have gotten done. Yeah. So chapter 2, yeah, here we go. So we left off talking about dimensional analysis, problem solving, unit conversions, right? We got through this here, with this being our skeletal. So as far as, plug my Wacom pad in. So information given times some sort of conversion factor will always yield, if we've done it correctly, the information sought. Given unit multiplied by a conversion factor set up in such a way that the given unit sits at the bottom, the desired unit sits on the top, and then the given and the desired will cancel out, which we like. We want to end up with, or the given units will cancel and we'll end up with the desired unit. So a conversion factor like, for instance, 2.54 centimeters equals 1 inch can be written with either 2.54 centimeters on top, 1 inch on the bottom, or you can, I believe the next slide shows it, you can flip it. So here we go. So either one of these is applicable. It, depending on which one you use, it has to do with, are you trying to get rid of inches and move into centimeters, or are you trying to get rid of centimeters and move into inches? So the charts here, or the slides here, specify making a solution map, which you'll see me do, where I sort of write what I'm starting with, where I'm ending, I put boxes around it and an arrow. So problem solving, identify the starting point, identify the ending point, critical think to figure out how you're going to get there, maybe use a solution map, sort, strategize, solve, and check. Okay, so let's do a couple of these. So using dimensional analysis, how many seconds are in 34.02 days? So I'll give you guys a couple minutes. I want you to start, write out what your given is, what you're trying to find, maybe a solution map. So how can I go from days to seconds? Maybe that's not a direct thing. So I need to take some hops in between because days and hours and things like that. Okay, just another 30 seconds. All right. So for this guy here, we've got our given information of 34.02 days. And I'm trying to find seconds. Now, again, this may be something that you can sort of do in your head because you use days, hours, minutes, seconds so quickly and throughout your life, but I really want you to set it up in dimensional analysis so that when a problem comes up where you like, I don't know that off the top of my head, you can still get the answer correct. So we start with our given information, or actually let's make a flow chart. So I don't know how many seconds are in a day. You may be one of those people that knows those like random facts that there are this many seconds in a day. I have no idea. But I do know, if I do days, I do know how many hours there are in a day, right? Doesn't feel like it's 24. Sometimes it feels like it's 6, but there's 24 hours in a day. And then I do know that there are 60 minutes in 1 hour. Sorry, let's not even put the 60 in. I'm just going to put minute and then minute to second. Okay, so that's sort of my hop chart. There's 4. Now, yes, there's 60 in there. So I'm going to fill this in with 1 day is equivalent to 24 hours. 1 hour is equivalent to 60 minutes. And 1 minute is equivalent to 60 seconds, right? So starting with our given 34.02 days, I want to get rid of days. So for every 1 day, I get 24 hours. That gets me to the first step. Now I want to go from hours to minutes. So I want to get rid of hours and get into my minutes. And we know for every 1 hour, we've got 60 minutes. And then last one, I want to go from minutes to seconds. So I'm going to put minute on the bottom, second on the top. For every 1 minute, I get 60 seconds. And the way that I've set this up is that this will cancel with this, then this cancels with this cancels with this, and the only thing left is the desired unit that I wanted, seconds. So then I can just plug it into my calculator, and I don't have to think, oh, so am I multiplying by 24 or am I dividing by 24? Am I multiplying by 60 or am I dividing by 60? I just let the dimensional analysis say, hey, everything actually is sitting on the top for this one, so we multiply. So 34.02 times 24 times 60 times 60. Okay, so I ended up with 2,939,328. And this is seconds. I am going to refine this a little bit for significant figures. This thing has 1, 2, 3, 4 sig figs, so I'm allowed to keep the 2, the 9, the 3, and the 9. The 3 will tell this 9 to round or to stay. So 2, 9, 3, 9. Then I have to fill in zeros, seconds. And then why not, while we're at it, let's just put it in scientific notation because it's good practice. The decimal lives here next to the 0. I want the decimal over here to give me a number between 1 and 10. So I'm going to hop 1, 2, 3, 4, 5, 6 hops, 2.939. I don't include the zeros because they're not significant. I just include the block of significant numbers, times 10 to the, remember this is a big number that we're representing in a smaller way, so big numbers get a positive exponent, 6 seconds. So hopefully you guys are all starting to see how dimensional analysis can be used like really anywhere with any sort of conversion factors. We can do it for transfer, if we're trying to transition in units of energy, if we're trying to transition in units of length, volume, all sorts of different things. So let's do, I think I've got, I had a formula sheet, but let's just do, we'll do another one. Okay, so. many grams is a woman who weighs 125 pounds? Okay. How many grams is a woman who weighs 125 pounds? So usually, I believe the textbook has a conversion factor sheet in the back of it. Your lab manual also has a conversion factor sheet. When in doubt, you can always Google conversion factors, okay? So grams to pounds or pounds to grams. Just to clarify, you want to round to the same number of sig figs as the given. Yes, because the conversion factors assume unlimited number of significant figures. So yeah, with conversion factors or with converting problems, dimensional analysis will go with the given information. All right. So this guy, pretty simple in that it's really just a one-stepper. So I've got my given, and we've got someone who's 125 pounds. Find grams. So pounds straight over to grams. There is a conversion factor. So 1 pound is 454 grams. So we can just go ahead and start with our given, 125 pounds. We've got this relationship. I don't want to put grams on the bottom. Like, I'm actually going to write it how sometimes I'll see students, they'll go, okay, so 1 pound is 454 grams. This is why the dimensional analysis helps, because you can see right here, I can't cancel. What I would get is units of pounds squared divided by gram. You don't like that. So this thing needs to get flipped. Another mistake that I see, which actually I have done as well. So if you see it, just stop me and say, yeah, I think those are wrong. Is they do get pounds on the bottom, but they say something like 454 pounds is equal to 1 gram. That logistically does not make sense, right? Like a gram is a very small amount. It definitely doesn't contain 454 pounds in it. Okay, so that's another one where we get the magnitude with the wrong unit. So don't do that either. So at the end of this all, what do we really want? We want 1 pound is equal to 454 grams. Cancels, we'll be left with unit of gram and a relatively large number. Okay, 56,750, and I get 3 sig figs. So I'm gonna say 56,800 grams. Questions? I hope that this feels easy. I want it to feel like simple. Like I want you to feel like, oh, this is sort of remedial. Like she keeps going over this because I want you, because then when you're sitting at the test, you can be like, oh, this is easy, or at least this isn't terrifying. Okay. So we will, we're going to move forward, but conversion factors are going to come with us. This whole process is going to come with us into the next chapter as well. So we will definitely see this again. Okay, so they had a problem in here where they were going from centimeters to feet. They said, hey, if you have 194 centimeters, what is that in feet? And you do a 2-step, right? So you know centimeters into inches, and then you know inches into feet. And we can get our final value. Here we would only want to round to 3 sig figs, excuse me. And I don't know why they didn't round to 3 sig figs, but they should round to 3 sig figs. Here's another one. This is a dual step. So let's say that you've got 48.0 miles to the gallon, right? And we want to get this into kilometers per liter because we're not in the States, we're traveling through Europe, and then we rented a car. So you have to think of these 2 units separately. So 48.0 miles for every 1 gallon. The mile is on the top of the fraction bar, the 1 gallon sits on the bottom. So the first thing you can do is convert your miles into kilometers. So I would multiply this by a factor of 1 mile is equal to 1.609 kilometers. You could also do 1 kilometer is equal to 0.62 miles. Either one would work. And what you'll see is that the mile will cancel, right? And we'll be left with units of kilometers. Now, the second thing we want to do is get rid of the gallon, and we want it to be per liter. So on the bottom, I want this to be per liter, all right? So I need my gallon, or what I'm trying to get rid of, to be opposite. So I'm actually going to put the gallon unit up on top. So here we have 1 gallon is equal to 3.785 liters. This is doing the opposite of what we've normally done because normally our unit sits on the top, right? But here we've got a unit sitting below the fraction bar. So gallon is below. Here you put gallon above, the gallons will cancel, and you'll be left with liter below the fraction bar, which is exactly what we want. We want kilometers per liter. So you may see one of those or 2 of those on the homework. I don't put them on the tests. Suzanne, did you have a question? No, you're just saying hi. All right. When converting quantities with the units raised to the a power, the conversion factor must also be raised to that power. Yeah. So let's say we've got this. Let's say we have this conversion factor. 2.54 centimeters is equal to 1 inch, okay? But let's say we're not dealing with centimeters and inches. Let's say we're dealing with volume. So we're dealing with centimeters cubed to inches cubed. And we want to figure out how to, like we don't have that conversion factor off the top of our head. So in order to do that, what we would do is we would literally just cube each side, okay, which is what they did here. The cube gets distributed both to the number and to the unit. Number and unit. So now we have 2.54 cubed, centimeter cubed, which is the unit that we were going for, is equal to 1 cubed, and then inches cubed. Anything, any 1 cubed to the third, to the second, to the 18th, it's always going to be 1 because you're just taking 1 times 1 times 1. So 1 inch cubed will now equal the 2.54 cubed, or 16.387. So that's a way that you can derive a cubed value from a, like, just basic centimeter to inch. And then as far as doing a conversion, it's the exact same thing. So now we've got a new derived conversion factor, this thing here, that is talking about volume. Because remember, length times width times height gives us a volume or a space. So if we had 100 or 1,255 centimeters cubed, and I wanted to know what this was in inches cubed, we could use this new derived conversion factor right here. You set it up the same way. You put the centimeter cubed on the bottom because we want that to go away. We put the inch cubed on the top because that's where we want to go. And we just let the dimensional analysis tell us what to do. So this number times this number divided by our 16. We get a final answer with just the inch cube unit, and then we round accordingly. So that's just a quick trick if you are ever trying to use a cubed value, or and you don't know the conversion factor off the top of your head. Okay, so there's one more. Oh, excuse me, man. I just cannot wake up this morning. There is just one more thing from this chapter that I want to talk about, which is density. It's down here. So density is a physical property, and we'll get more into physical properties and chemical properties later, but really a physical property is just something that matter or an object can show you or express without having to change what it is, right? So a piece of metal, when you measure its density, it doesn't have to become something new in order to show you the density. So why do some people pay more than $3,000 for a bicycle made of titanium? I would say because they're crazy, but it has to do with density. Now, a lot of times what people will say is, oh, well, they're spending, 10 grand for a bike because the bike is lighter. The bike is lighter, but is it like a teeny tiny, like little bicycle made for ants, right? That's a really light bicycle. That wouldn't be a very useful bicycle. So what you want is you want a bicycle that's the same size, it's human size, but it weighs less for that volume. So it has what's known as a lower density. It makes you go fast. It does. It does make you go fast. But actually, I remember Lance Armstrong, though, saying one time, he was like, not that he's got any credibility anymore, but he said something like, they asked him, what piece of equipment is the best for riding a bike? What can you do to go faster? And he's like, lose 5 pounds. That will make you go faster. It's like the fastest way to go faster. So the bike, yes, you can buy the $10,000 bike, but you probably be fine with the $2,000 bike. It's slimmed up a little bit. So, okay, so back to density. So what density is saying is that we have the same volume or the same shape bike, but it has less mass in that same shape. So titanium, for instance, would have 4.50 grams per centimeter cubed. which is less dense than an iron bike, which would be 7.86 grams in every centimeter cubed. So more material, more matter in the same volume. So let's get into what density is. Not mass times volume, but density equals mass divided by volume. Okay, that is our density equation. When we give you an equation like this that has 3 variables, you will always be given how many? You'll be given 2 of the 3. You'll be asked to solve for the third. So I could give you mass and volume and you solve for density. I could give you volume and density and have you solve for mass. I could give you mass and density and have you solve for volume. So you're definitely going to want to be able to isolate variables. I'm going to isolate these variables. I'm going to spend about 5 minutes working on isolating variables. After that, we can have a private meeting, or you can go to the tutoring lab to work on isolating variables. Okay. All right, so if I have this equation, density equals mass over volume. Now, let's say that I want to solve for mass. So I've given you density and I've given you volume, and I just want to know what the mass is. We can't plug it into the equation set up this way. I mean, you can, and then you could isolate after the fact. Some people like to do that, put the numbers in and then isolate. I'm going to isolate beforehand. So if I want to get mass by itself, what I need to do is I need to take volume and somehow move it to the other side of the equation. Now, on this side, volume is acting as a divisor, or it's underneath the division bar. So in order to get rid of it or move it to the other side, I have to do whatever the opposite order of operations is. So if it's dividing here, I need to multiply this side by volume, because if I multiply this side by volume, volume and volume disappear. But if I'm doing it on this side, whatever I do on this side, I have to do over here. Okay, so now volume cancels and we're left with, I'm gonna flip these places. Mass is now equal to density times volume. Okay? So I've isolated it. Going back to the original here, density equals mass over volume. If I want to solve for volume, okay, I want to get this guy down here. This is a little bit different because it's below the fraction bar in the starting point. So what I tend to see students do a lot in this is they'll go, oh, well, I'm going to divide by mass on both sides. My masses cancel, and now I have mass times density equals volume. That is not correct. Okay, why is that not correct? Well, you can do that. You can divide by mass on both sides, but what is volume doing? Volume here is still under the fraction bar. So the correct way to write this would be, oh, sorry, I was dividing anyway. So this was incorrect in multiple ways. Let's erase this. So that was incorrect. But then also density, so I get this a lot, density divided by mass equals volume. So this is incorrect. The reason it's incorrect, again, is because volume doesn't just all of a sudden pop up on top of the fraction bar. So we don't like this. What is actually happening is density over mass is equal to volume below the fraction bar, right? So to finish this off, because I don't want the inverse of the volume, I want volume, I have to flip-flop these. So mass divided by density is actually equal to volume, not density divided by mass. If you're like, oh, it's close enough, right? No, those will definitely give you different numbers. Another way You can solve for this just so that we can sort of get comfortable with isolating variables. Density equals, I don't want that shape, density equals mass over volume. I can see here volume's on the bottom, and I know that I'm not gonna like that, so I'm gonna actually move volume to the other side. So now I have volume times density equals mass, because these have canceled. Then from there, to get volume by itself, I'll divide this side by density and divide this side by density, and I get volume equals mass over density. This is the same thing as this, right? So two different ways to solve it. You can figure out whichever one works better for you. Isolating variables is going to pop up throughout the semester. All right, I think that the biggest equation you have is maybe next chapter Q equals MCAT. I think it's 4 variables. I don't think we'd really go, well, no, gas laws towards the end, we get more than 4 variables. So you will want to know how to isolate. Okay. So that's my 2 cents on isolating variables. Go back to here. So here's a problem. It says, calculating density. So we calculate the density of a substance by dividing the mass of a given amount of the substance by its volume. So let's say we have a problem here where we have a volume of 22.5 milliliters and a mass of 27.2 grams. And I say, what's the density? Well, in order to get the density, you need to use both of those values. We'll put the mass on the top. So starting to get comfortable with gram is talking about mass, milliliter is talking about volume. It doesn't specifically say it wants it in any units, so we can just keep the units as is. What you'll find is that when you divide these two, gram doesn't cancel with anything and milliliter doesn't cancel with anything. Both of those units stay around, which is what we want, right? Because at the end, our value should be a unit per unit or a mass unit per volume unit. That's what gives it the density quality. Sometimes I'll have students plug this in and they'll get the 1.21 and then they'll say it's 1.21 grams. That's a mass value though. That's not telling me anything about density. I need to know how many grams that is in every 1 milliliter. And when this is written, this density, you can think of it as being written as, so 1.21 grams for every 1 milliliter, okay? There's sort of an inferred one on the bottom thing. So the number always goes with the top unit. A 1 will go with that bottom unit. And hey, look at that. If you see, we've got 2 units. Anytime you have 2 new units or a unit over another unit, it becomes a conversion factor. So we can sort of use density as a conversion factor as well when we're calculating. And I'll show you guys that. Let's, all right, so the solution map for this, you've got a problem, mass times volume, or mass and volume, and you want to find density, use the equation. I don't want to do this one just yet. I want to give you just a straight density one. Silly bar, always in my way. Okay. What is the density of a metal bar with a mass of 14.02 grams and takes up 300. Now let's go with, no, I'm gonna go with something smaller, 5.6 0.76 milliliters. What is the density of a metal bar with a mass of 14.02 grams and takes up 5.76 milliliters? Okay, so this guy here. So what is the density? And when I was in school, I would always like write all over my tests. It might be a little bit more difficult because you guys are going to be doing them online. But I would always write and like annotate all over everything, like circle things, just to give me an idea of like, you know, like what's going on in the problem. So here I've got two given pieces of information. I know that I have 14.02 grams, and I'm going to remind myself that that's equal to the mass because it says it right there. I have 5.76 milliliters, which is a unit of volume, and I'm trying to find the density. So I know density equals my mass over my volume. I have this, check. I have this, check. I have this, check. And I am left-handed, so if you guys are like, why are your checks backwards on assignments and stuff, that is why. Okay. So I know my mass is 14.02 grams. I know my volume is 5.76 milliliters. So I'm gonna just plug that in. Two, 5.76. And I end up with 2.43, and I'm going to go with 3 sig figs because the least precise is 3 sig figs. And I'm going to keep both units intact because neither of them canceled, right? So it's grams per milliliter. Units just as important. Any questions on that? You can throw it in the chat, or you can unmute yourself and just say, hey. Okay, so let's go to the slides and try just from a different angle. So I want you to try this one here. For a liquid substance with a density of 1.32 grams per centimeter cubed, what volume should be measured to deliver a mass of 68.4 grams? This one's a little bit different. I want you to try it before I explain it. And I'll explain it in two different ways. Yeah, this is my Frenchie, and he brought him over because of density, because he's very, very dense. He's a good example. He is not very big, but he weighs 40 pounds. He was supposed to be a teacup Frenchie. That's why I spent more money on him. They said he was going to be 18 pounds. 40 pounds later, he's a beast. And I love dogs. So if anyone ever wants to show me their dog, please do, because I like dogs way better than people. Animals in general, better than people. Okay, so let's look at this density problem. Let me put my annotate on. Or warn you, when I use the annotate button within Zoom, it's a little shaky. But all right, so we have the density. So we're given density. And we also know this is the density, 68.4 grams is the mass. So we're trying to solve for volume. We're trying to, find volume. Two cute dogs. Yeah, I want to see them. Seriously. Anytime after class, show me some pups. All right, so how we can solve this, one way is to plug it into the equation. So I know that density equals mass over volume. So then I know that volume equals mass divided by density. All right, if I get my mass divided by density, that'll give me the volume. So I can plug it in. Mass on the top, 68.4 grams over 1.32 grams per centimeter cubed. Now, I like to, when I plug it in, again, I like to put my units in because it lets me know that I've done it correctly. So, I end up with what, 51, we've got 3 sig figs, 51.8. And then as far as units are concerned, it's asking for volume. I just know that like this is a volume unit, centimeter cube, but you can look here what happens to grams. There's a gram here and there's a gram here. So gram cancels. Centimeter cubed is below this fraction bar and it's below this fraction bar. Anything divide makes it actually multiply up on top. So we can use centimeters cubed as our unit. Another way you could technically do this is to use density here, this thing, as a conversion factor. So I start with my mass, 68.4 grams, and I plug it into dimensional analysis where I'm going to use the density as the conversion factor. Now this 1.32 grams per centimeter cubed, I want the gram part to be under the fraction bar, the 1.32 gram, and then that's for every 1 centimeter cubed. You notice we're doing the same thing that we were doing here. What happens to the units of grams? They cancel and you should be left with centimeters cubed. You get 51.8 centimeters cubed. So you can do it either way. I tend to see students just like to plug it into the equation. Then they don't have to worry about this. That's fine. You don't have to do it as a conversion factor. Just make sure you're getting your units canceled correctly. Questions on that? Okay. Here's a table of some common substances and their densities. So water in general tends to be like our starting point or our reference point for a lot of these things. So gram per centimeter cubed, 1 gram per centimeter cubed is equal to water. Okay. So things are always kind of in reference to either being more or less dense than water. Ice has a density of 0.92. Ice is water is one of the few substances out there where its solid is less dense than its liquid. Usually solid things become more dense than their liquid versions, but water, when it's in liquid form, the particles or the molecules are actually able to compact more than when they're aligned in their solid form. That is a very important component of life. It's the reason that lakes freeze from the top down and life can stay underneath. It's a super, super important thing. Lots of consequences because of that are useful. You look at oak and charcoal and ethanol. Those are also lower density than water, which means that all those things are going to float in water. If you don't believe me on the ice thing, we'll put an ice cube in your cocktail and you'll see that it floats at the top. Things that are more dense, glass, aluminum, titanium, all the metals are going to have a more dense quality to them. Okay? Platinum, really expensive material and also very, very dense. Okay, so in order to make a platinum ring, looking at these two things, a platinum ring is going to require a lot more platinum than if you were to make a gold ring. So you need more of the platinum. So not only is platinum expensive, but you need more of it in order to make the same shape ring. Okay, so I'm going to do one more density problem because why not? Let me just clear this up. All right. Okay. What is the mass of 6 liters of a gas with a density of 0.032 grams per milliliter? All right. So this one seems like a relatively straightforward density problem. Given I have 6 liters, which is talking about volume. I have 0.032 grams per milliliter, which is talking about density. I'm trying to find my mass. Okay. So this is where you've got to start to look at the details. Hopefully some of you realize that this is in units of liters, and this is in units of grams per milliliters. These two units are not matching up, okay? So if I was to plug these into my density equation, liter and milliliter will not cancel with each other. So what we need to do is get these into the same units. So I would say let's get liters into milliliters. Some people will say, oh, well, can't we make it in grams per liter? If you want to change density into grams per liter, you're more than welcome to. This just seems like the easier path. So first I need to get all the same units. So 6 liters is equal to 6,000 milliliters. King Henry died before drinking chocolate milk. We've got to go from king to before, 3 hops, decimals here, 1, 2, 3, fill it in with 3 zeros, okay? So 6,000 milliliters, now we have the same units. Now we get to plug it into our equation. Density equals mass over volume. I want to get mass by itself, so mass equals density times volume. Because we multiply volume, those will cancel, and we're left with that. So I should be able to get mass by taking the density, 0.032 grams per milliliter, and multiplying it by my volume, which is 6,000 milliliters. Okay, I like this because there's a milliliter, and underneath this fraction bar is a milliliter. Those are going to disappear on me. Okay, 0.032 times 6,000. So your mass is equal 192 grams. And this is where it drives everyone crazy. How many significant figures do I get to use? Put up a finger. 3? Huh? 1. We only have 1 sig fig. There's 2 pieces of information here. How many sig figs does this thing have? This has 2. 1, 2. How many does this have? That's a crappy piece of information. 6 liters. What do I mean? Like, oh, whatever. He has like 6 liters roughly. If I was being precise, I would say, no, it is 6.00 liters, but I did not say that. So you get 1 sig fig. Oh man. Okay, so we get to keep the 1. What does the 9 tell the 1 to do? Tells it to round up. So 200 grams. We round, yes, we round. So we round to 1 sig fig, so we get 200 grams. Ugh, that's so frustrating. It is what it is. So at least on this first test, be really anal about significant figures. My care for sig figs drops drastically as the semester goes on, okay? Because I just want you to get the answer right. So don't worry so much about sig figs then. Cool. So we're going to leave chapter 2. In the next couple minutes, we're going to hang out in chapter 3. So that's all of chapter 2. Done. Exit out of here. Okay, it doesn't want to X out. That's fine. Don't have to. Something. Okay, so chapter 3 is a little bit more concept-based. There's some math towards the end. This whole chapter is looking at matter and energy. So when we think of the universe as a whole, we kind of divide the universe into either being matter or energy. Matter is the stuff, Energy is what makes that stuff interesting, what gets it to do something. So atoms and molecules in your room. Everything that you can see in your room is made of matter. If you can see it with your eyes, you're picking up matter with your eyes. There are different kinds of matter, and matter are related to different differences between the molecules and atoms. So when you see a cup of water versus a pen, those things are made up of different molecules and atoms that are giving, on the microscopic scale, those molecules are then giving different properties on a macroscopic or a human scale. So this picture here shows us water molecules on the left. They are H2O, and they're not bonded together in a solid form. So we have a liquid, so that has certain properties. This is really useful for hydrating, right? Over here, we've got a golf club, okay? So this golf club is made out of graphite. It is made just of carbon atoms that are in a solid form, all right, which is giving it, this golf club, its specific properties. This is not good for hydration. Right? You can't drink it because it's a solid. So macros or microscopic stuff gives us these macroscopic qualities. So what do we define matter as? It's defined as anything that occupies space and also has a mass. So you have to have those two things. Some types of matter we can see with our eyes. So steel, water, wood, plastic. We can see those things with our eyes. So we can say, yeah, it's pretty obvious that it has matter. But there's other things that do have matter that we can't necessarily see with our eyes. Air, microscopic dust, small scale things. Either small scale things or really low density things our eyes can't pick up, but we still say that there is in fact matter there. So air, everything around you, you can't see it, but something is there because you're breathing it in and it's keeping you alive, right? Another way that you can sense that air is a real deal thing is when you're driving in a car and you stick your hand out the window, you can feel that air resistance. Lets you know that there is in fact matter there. It's just that our skin doesn't pick up that sensation when we're just sitting in the room. Maybe if you have a really strong fan, you'll feel it. So matter is composed up of atoms and molecules. Matter in general on our scale, on a human scale, it can feel smooth, sort of smooth and continuous. So if you take your hand and you run it across your desk, it feels like it's a smooth, solid, right? We have this idea that matter is sort of a solid thing, but it's actually not. If we were to take matter and we were to break it down into smaller and smaller pieces, at some point we would break it down to a fundamental particle known as an atom. Atoms are the building blocks of matter. So just like letters are the building blocks to words and sentences and stories, atoms are the building blocks to compounds and material. Because of the nature of most atoms, they tend to be unstable by themselves. So they like to bond together with other atoms to form molecules. So just like us as human beings, we do better, well, not all of us, but a lot of us do better when we're coupled with another person or a community. Atoms as well tend to do better in a coupled version, which is known as a molecule. In order for it to be a molecule, it just needs to have 2 or more atoms joined together. And it has to have a specific geometric arrangement. So water is an example of a molecule, right? H2O. How do we know it's a molecule or a compound? We would be able to write a chemical formula for it. And then recent advances in microscopy have allowed us to image the atoms and molecules that compose matter. Yeah, so we can use electronic microscopes and things like that to actually see the shape of the individual atoms. So independent atom particles So all matter is ultimately composed of atoms and substances such as aluminum. The atoms exist as independent particles. So here we've got an aluminum can. It's in solid form, and all the aluminum atoms are just stacked together. They're in a crystalline shape, but they're not like fused to each other, any sort of diatomic quality. So they're independent aluminum particles or atoms. If we look at a bottle of isopropyl alcohol or rubbing alcohol, this liquid is not free atoms floating around, it's molecules. So there's these little packets of isopropyl alcohol molecules. And this molecule is made up of a certain amount of carbon, hydrogens, and oxygens. And you know, the more of these little things you have, the more rubbing alcohol you have. But in order for it to have the properties of rubbing alcohol and behave like rubbing alcohol, it needs to be these little guys in there. All right, let's go over that. So the common states of matter. So when we're talking about matter, there's three states: solid, liquid, and gas. There is actually a fourth state of matter, which is known as plasma. And a lot of the universe is actually composed of plasma. But we aren't going to talk about plasma in this class. If you want to learn more about plasma, you can go take like a physics class or an advanced physics class. But for the sake of this class, we've got solid, liquid, and gas. Water is a really cool material in that on the surface of Earth, we can find it in all three phases. We find it in solid ice, liquid water, and steam gas or water vapor. All right, so we're going to stop there. Just FYI, we are not meeting for class on Monday, so don't log in on Monday at 8 a.m. I'm sure it won't be difficult to miss that. But we will meet up on Wednesday. Make sure you get that lab done though. I would do it now or sometime in the next couple days. I'm around by email today, tomorrow, and like part of Friday. I check my email on the weekends, just not as regularly. So. Oh, other thing, I have been getting so many emails, So if you've sent me an email and you haven't gotten a response, just say, oh, hey, what's up with this? If it's been like more than 24 hours, to bump it up to the top of my list, because I have had an email or two get lost down in the ether of my inbox. So just pop it back up for me, okay? Otherwise, you guys have a really good weekend. Email me if you have questions, okay? Bye, everyone. And you can stay around if you do have an individual question too. I'll be here.
We have a quick question.
Yeah, hold on one second.